Hello students, in this video we will be talking about the frequency compensation technique to stabilize the multipole open loop system. Okay, so we are going to modify our open loop system so that when we have any feedback around it, the circuit stays in a stable condition. Okay, so this particular slide talks about the need for compensation. So typically open loop system contains many poles in it, right? And when we put such kind of system around a feedback, we might tend to have our system to get into an unstable condition, correct? So this compensation is basically a technique such that it modifies the open loop transfer function so that for any kind of feedback that we have, the circuit will always stays inside the stable system. Okay, now what is the rule through which we can attain this kind of condition? The rule is basically our Bar-Cousins criteria. Okay, so what it says is, for a loop gain that is equal to 1, or the magnitude of the loop gain when it is equal to 1, we need to have the phase value of the loop gain that's supposed to be greater than minus 180 degree, right? So in this, for any value of beta factor, as we know that this beta or the feedback factor could range from a value of 0 and it can go all the way up to a maximum of 1, right? So for any range of beta, the loop gain when it is having a magnitude that is equal to 1, and when we need to ensure that the phase value that is read is greater than minus 180 degree. Okay, so let us consider a kind of open loop system where it has 3 poles in it, and this is the kind of response, the magnitude response we have that has been plotted here. Now clearly this graph shows that for a feedback factor that is smaller than the value of beta 1, then the system would ensure that they are under stable condition, right? So how did I say that? In this, there are dotted lines that represents the closed loop transfer function, right? And by looking across our loop gain, which is nothing but the difference between the open loop transfer function and the closed loop transfer function, right? So when we are at frequency that is at 0 hertz or 0 radians, what happens is we have a loop gain magnitude which has this as its magnitude, right? Now that is a frequency which is known as gain crossover frequency. It is the frequency at which this loop gain magnitude becomes 0 dB or becomes 1, right? It is across this particular frequency we have this loop gain becomes 1, and this is termed as omega gx. Now when we have the phase value that is greater than minus 180 degree at omega equals to omega gx, then we say that the system is stable, correct? Now in this case we have a beta the factor that is equal to beta 1, and for this when we try to read the phase value at omega equals to omega gx, we found that this particular phase gives us a value that is equal to minus 180 degree. As we know, under this condition this closed loop system will eventually get into unstable condition, right? So for values of beta that is smaller, for values of beta that is smaller than the value of beta 1, then the system will be at a stable condition. Okay, but for value of beta that is greater than or equal to beta 1, then the system would be driven into unstable condition, right? So what is the worst case value that we can have for beta? As we know, let me try to plot the range of beta that we can have. So for beta equals to 0, which means that we have an open loop system, but as we increase the value of beta right from 0 all the way equal to 1, then eventually we would have our closed loop magnitude plot being plotted across the 0 dB line, right? So what we know is the closed loop at DC could be returned as something like 20 log into 1 upon beta. And now if the value of beta is equals to 1, then this ratio becomes 1, and 20 log of 1 would return us a 0 dB, right? So our closed loop magnitude would lie across this 0 dB line. And when we try to measure the loop gain magnitude, it exposes all of this open loop transfer function, right? So all of this shaded line, or the difference between this entire shaded graph, would tend to appear as a loop gain magnitude, and we will have our gain crossover frequency at this particular intersect. True? Even for a feedback factor that is equal to 1, which is the worst condition that we can have, when we try to read the loop gain phase value at omega equals to omega gx, we need to ensure that the value that we end up should have a phase value that is greater than minus 180 degree. Correct? Basically, the compensation technique talks about like how to modify the open loop system, and when we have a feedback factor that is equal to 1, we have to ensure that the phase value of the loop gain has a value that is greater than this minus 180 degree. Okay, so that is what we have to ensure when we try to apply a compensation. Okay. So let's do that. So there are basically three major techniques in order to compensate the open loop system, so that even for the worst condition, for having a beta that is equal to 1, we will have a loop gain phase value at omega equals to omega gx to be greater than minus 180 degree. Okay, so out of these three techniques, we will be talking about the first two. The first one is add a dominant pole. Second one is move a dominant pole. The third technique will be posted later, and people who are interested can go through it. But the first two techniques are there for the syllabus, so I'll be doing in this particular video. The first method, that is nothing but add a dominant pole, is the most simplest and the most commonly used method. Now, in order to talk about this method, we are going to have some of the considerations. The first one is assume that we have the worst case feedback around the open loop system that we are going to talk. What I really mean by the worst case scenario, having a value of beta that is equal to 1 would ensure that we are at the worst case condition, correct? And we also mean to ensure that at least a phase margin of 45 degree at omega equals to omega gx. Okay, so let us see how do we do all of these things by having an open loop system having such kind of magnitude plot and a phase plot. Okay, so before I really start, open loop y-axis lying somewhere at the center of the frequency. Okay, so you can really scale this particular y-axis values towards the left hand side. Okay, so these are basically lying towards the left side, and all of the frequencies that we are talking, even this frequency that we are talking, is basically the positive quantity. Okay, so do not get confused just because we have something at the mid value, and anything that lies towards the left, do not consider them as a negative values. Okay, so this is a kind of confusion that we have across this particular slide, but please ensure that you are not getting confused. Okay, yeah. So now let us come back to our subject. So having a beta that is equal to 1 would create a worst case feedback around this open loop transfer function, correct? Now, when we have a beta that is equal to 1, where exactly our closed loop magnitude plot would lie? It would be at 0 dB, right? So what happens is, when we try to plot our closed loop magnitude plot, this plot would appear at 0 dB, right? And what happens is, this entire open loop transfer function that we had would be exposed to the loop gain magnitude plot. And where exactly would be our omega gx or gain crossover frequency? It is the intersect between the open loop and the closed loop, right? So it would be at this particular frequency we would have this omega equals to omega gx. But our goal is to ensure that when we try to read the phase value at omega equals to omega gx, we need to have a phase value such that it end up having a phase margin that is equal to 45 degree. What is the phase value that we need to have? So in order to get the information about the phase value, we need to know what is the definition of our phase margin, which is defined as 180 degree plus the phase angle at omega equals to omega gx that has been extracted from the loop gain. In this case, we have a phase value at omega equals to omega gx as something that is almost closer to minus 270 degree, which is a value that is far smaller than our minus 180 degree, right? Yeah. If we want to have a phase margin that is equal to 45 degree, then we need to have a phase value that is supposed to be equal to minus 135 degree, right? So when we try to read the phase value at omega equals to omega gx, we need to ensure that the phase value that we are reading here is supposed to return us minus 135 degree. But what we are getting here is minus 270 degree, right? As the name suggests, we need to ensure that we are going to add a kind of dominant pole in our system such that the phase value that is read at omega equals to omega gx should return us this value, right? Yeah, so how do we do that? We need to add a dominant pole. Okay, this phase value we need to achieve by looking back into our phase plot, correct? We want to have our frequency omega gx such that when we have our omega gx at a particular frequency, we would get a phase value that is equal to minus 135 degree, right? So which means that we need to have our omega gx somewhere here instead of the normal position, right? So we need to shift this particular omega gx to a new value. Now how would we do that? Because it is the value at which the open loop gain becomes a 0 dB, right? So which means that we need to have an open loop having a kind of slope, something like this, right? I need to have a pole at this particular intersect, and when we have a pole, the DC gain would degrade at a rate of minus 20 dB per decade, and when it degrades, it will step down to the first pole, right? So which means that we need to have a dominant pole that has to be added by through some mean, okay? And when we add a kind of dominant pole at this particular frequency, then it ensures that when the open loop transfer function will have a magnitude that degrades at a rate of minus 20 dB per decade, and all the way eventually it intersects at this particular frequency. Now when we have a kind of closed loop system, okay, for a value of beta that is equal to 1, then what happens is we would end up having our closed loop transfer function at 0 dB, and they both get intersect at this particular frequency. That is, this entire graph would be exposed as a loop gain, correct? And we have this loop gain that is equal to 1 or 0 dB at this particular frequency. And when we read the phase value at this particular frequency, we end up having a phase value that is equal to minus 135 degree, which is greater than the value of minus 180 degree. Okay, and that's how we can attain this phase margin of 45 degree. So let us see across the phase plot. So we had originally the phase being shifted from 0 degree to all the way to minus 45 degree at omega equals to P1, right? So now let us see what happened. Okay, so since we have added a dominant pole at a lower frequency, this has added this minus 45 degree at much earlier stage, and then the graph or the dotted line represents the new phase value after the addition of this dominant pole to our system. Okay, yeah, so it's a kind of review. Add dominant pole method is the most simplest method, but this involves a direct sacrifice of the frequency capability of the open loop transfer function. Okay, that is, if we remove a feedback, the basic amplifier, that is nothing but our open loop transfer function, will have a unity gain bandwidth which is of only omega p1, right? Which is much smaller than our previous unity gain bandwidth, correct? So if a feedback is applied, then the loop gain now begins to decrease at omega equals to PD. So what is PD here? That is, it is at this particular frequency, the loop gain magnitude starts degrading. That is, all this blue shaded graph represents that, right? So that is what is being commented here. And in general, all of the benefits gets further decreased when we further reduce the loop gain. So what do I really mean by this reduction in the loop gain? So say for example, if we have a beta factor that is lesser than the value of 1, then we would end up having a further reduction in our performance, right? So this could be explained with this graph. So what happens is, ultimately, when we have a different value of beta, then for that particular factor of beta, we would end up having a closed loop over here, right? And our loop gain magnitude has got now reduced. Now, in a way, what happens is the bandwidth is further reduced. So here is where our omega equals to the gain crossover frequency will have, right? Correct? Yeah. So which means that our closed loop will have a bandwidth of this much. Okay, so it starts all the way from this particular frequency to a frequency that intersects with our omega gx. So that is the bandwidth of our closed loop system. Correct? So in a way, we have reduced the open loop bandwidth as well as we have reduced our closed loop bandwidth. So that is the drawback of this particular system. Now let us try to do an exercise problem. Okay, till now we have represented the open loop system transfer function as A of S, right? Now let us consider a real circuit, something like this. Okay, and let us calculate what is the value of this A of S, or this open loop system transfer function. The circuit here basically contains two stages, correct? And each stage has a single pole. So how did I state that? Since because we have a capacitance Cy and Cx, correct? So due to each of these capacitance, each stage introduces a single pole, correct? What we know is that the open loop transfer function, which is basically defined as small a of s, could be defined as something like the DC gain divided by the denominator polynomial representing the system poles, which is nothing but 1 plus es by omega p1, where omega p1 represents the pole due to one of the capacitance, and there is again one more capacitance, right? So that pole information is entered here as omega p2. Since we have two stages, the value of A0, or the DC gain of this particular open loop system, could be returned as a product of the DC gain of the first stage, which I took it as A1, and the second stage, which is nothing but A2. Clear? Let us evaluate each stage DC gain. For the first stage, we have a kind of circuit that has been encircled through this red dotted line. Okay, so let us try to compute what is the DC gain out of this particular circuit. Now what we know is, in general, the gain of the first stage could be represented as a product of the capital GM times that of the R out, right? Yeah, so let us compute what is the value of GM that we have out of this particular circuit. Now when we short this particular node to the ground, we know that when we apply a small signal input at cross Vin, and the circuit, since the circuit is symmetric, under this condition we will have Vin by 2 and minus Vin by 2 across the gate and source of M1 and M2, right? And due to which, what happens is, the currents that are flowing through M1 and M2 would be represented as GM1 by 2 times that of Vin. Over here, the current could be represented as something like minus GM2 by 2 times that of Vn. So all that we have learned already. Now, when we try to into this kind of current, one could say that the capital GM for this circuit, or the first stage, could be returned as something like GM1 by 2, right? And that is the value of GM that we would get out of this first stage. Yeah. So now let us try to evaluate what is the value of the R out. Now when we look up through the drain of our M3, what we know is we would end up having a value of RO3. But how about the resistance that we would have when we look across the drain of our M2? It would be equal to 2 times that of RO2. Okay, so we have already done such kind of problem in our previous lecture. So I would advise you to go back and look into the op-amp charter in order to visualize how do we get this twice the value of RO2 when we look across the drain of our M2 transistor. Okay, so thus we have an R out that is equal to RO3 in parallel with 2 times that of RO2. Okay, and that is the total R out that we have. Now let us see what is the value of the second stage DC gain for the one that I have encircled with a green dotted line. Now this circuit basically is nothing but a voltage follower, which means that the gain from the node X to the node Y will be approximately equal to 1, right? So we have the gain, the DC gain of the second stage, that is approximately equal to 1. So now that we need to compute the value of this GM 1, 2 and the value of the output impedance of the first stage, right? So given all of these parameter values, if you substitute, you would end up having the DC gain of the first stage to be equal to minus 10.4, okay? And so one could eventually write the open loop system transfer function as something like A of S, that is equal to minus 10.4 divided by the 2 poles of the system, right? Now let us try to compute pole frequencies that are created by both Cx and Cy capacitance. Now let us assume that omega P1 represents the pole frequency that is created due to our capacitance Cx here, okay? Now what is the pole frequency? What we know is the pole frequency could be represented as something like omega equals to 1 upon RC, right? This is a general case. So now let us look back over this node X. So the value of this omega P1 could be represented as 1 upon the R out, right? So the resistance that we have here is the R out of our first stage, which is equal to RO3 in parallel with 2 times that of RO2, and that is the resistance that we have, and the capacitance is nothing but our Cx. So once we plug in all of these values, one would end up having the omega P1 that is equal to 250 meha radian per second, okay? Now how about the pole frequency created by the capacitance Cy? This could be returned because the resistive component that we have across the node Y is basically the source impedance of our M4, right? So what is the source impedance, or what is the impedance that we have when we look through the source of our M4? It is nothing but 1 upon GM4, okay? And the capacitance value is just Cy. So the pole that is created across the node Y could be returned as omega P2, that is equal to GM4 divided by Cy. Now this would end up having a value of 7.3 giga radians per second, okay? And that is the pole frequency created by the capacitance Cy here. Since our omega P1 frequency is far lesser than the value of omega P2, then the omega P1 would act as a kind of dominant pole, right? Now let us visualize the magnitude plot of this open loop transfer function. So what we have is a kind of open loop, okay? So A of j omega over the y-axis, and that's being denoted in terms of dB, and we have an x-axis having the frequency in terms of log scale, okay? And the DC gain, when we convert this quantity, this would return as something like 20.34 dB as its DC gain, okay? Now we have a pole somewhere around 250 mega radians per second, and we have the second pole happening somewhere around 7.3 giga radians per second. Now what we know is the DC gain would retain its shape as it is till we reach the first pole. But once we reach the first pole, what happens is the gain starts to degrade at a rate of minus 20 dB per decade. But what is the value of gain when we are at omega equals to 7.3 giga radians? So we are not sure about that, right? But what we know is the line that connects between the first pole and the second pole will have a slope of minus 20 dB per decade. But we are not sure what would be the value at that particular frequency, right? So we don't know what is the y value at this particular point. So as we have done many problems, what we can do is, I know what is the point at this particular location, right? So I have y2 whose value is 20.34 dB, and I have x2 that is equal to 250 mega radians per second. So I know both these quantities at this particular point, whereas at this particular point what we know is our x1 value, correct? The x1 is nothing but our 7.3 giga radians per second, but what is unknown is our y1 value, correct? So let us try to figure out what is the value of this y1. From the line equation, we can express the line that we are trying to connect between these 2 points could be represented as y2 minus y1, and that's supposed to be equal to the slope times that of x2 minus x1, correct? Now what is the slope that we have is basically that is equal to minus 20 dB per decade. And what is the value of x2? It is nothing but it's equal to log of 250 mega radians per second minus what is the value of x1 here? It is equal to log of 7.3 giga radians per second. Okay, and the whole thing is multiplied with the slope. Now when we do all this computation, and we also know what is the value of our y2 here, right? And that is equal to 20.34. Okay, and this is our value of y1. So when we do all this manipulation, one would end up having a value of y1 that is equal to minus 9.187 dB. So how do we interpret this result? Which means that we have this line, okay, that is having somewhere its y value that is equal to a negative value, and that value is equal to minus 9.187 dB, right? And that is what this particular expression says. Okay, so now when we have a feedback around this open loop system with a feedback factor that is equal to 1, then it's obvious that the closed loop system will have its gain somewhere at 0 dB, right? And we expose all of this region as our loop gain magnitude. And where exactly our omega gx lies? It is at this particular intersect between the open loop and the closed loop. So this particular frequency represents our omega gx. Okay, and now again, what is unknown in this particular case is we know what is the value of y1 at this particular point, which is nothing but 0 dB, but what is unknown is our omega gx, which is nothing but our x1, correct? So again, we have a line that connects between these 2 points. This line runs at a rate of minus 20 dB per decade, correct? So we can still utilize the same formula. The only exception is here the y1 is right now is replaced with a value of 0 dB, and the x1 is an unknown, which we can write it as omega or log of omega gx. So when we do all of the manipulation, one would end up having a value of omega gx that is equal to 2.6 giga radians per second. Okay, now how to extract the phase information or the phase margin information? What we know is the phase margin is nothing but 180 degree plus the phase value that is read at omega equals to omega gx, correct? So how do we do that? What we know is the phase value of any frequency could be written as minus tan inverse of omega divided by the omega p1, which is equal to 250 mega radians, right? And the second pole could be written as something like omega divided by omega p2, where the omega p2 value is 7.3 giga radians, correct? Now what we wanted to know is to have the phase value at omega equals to omega gx. Okay, so at this particular frequency, when we plug in all of the frequency terms that we know, which is 2.6 giga divided by 250 mega minus tan inverse of 2.6 giga divided by 7.3 giga, one would end up having a phase value that is equal to around 104 degrees, correct? And what is the value of phase margin in this case? It would be closer to the value of 7.6 degree, right? Yeah. So let us look back to the second problem that we have. In the second case, we have to modify the value of Cy such that we end up having a phase margin that is equal to 60 degree for a unity gain feedback. Okay, how do we do that? So again, looking back into our case, what we wanted is a phase margin that is equal to 60 degree, which also means that when I try to read the phase value of the loop gain at omega equals to omega gx, we need to end up having 120 degree. Okay, and what is allowed here is to change the Cy capacitance and not our Cx capacitance, which also means that the value of this omega p1 will not change, because this omega p1 is a frequency that is related to our Cx, and we are not going to modify our Cx capacitance. But what we want to modify is our Cy capacitance in a way that it also modifies the omega p2 frequency, right? So what is omega p2 here? The omega p2 is nothing but gm4 divided by Cy. So we need to modify this particular pole. Okay, so when we modify this pole frequency, we need to end up having minus 120 degree. Hope you get this point. So I would advise you to work around this second condition in order to make sure that when you have a particular value of Cy, you need to end up having a pole omega p2. Okay, and when you substitute back into this equation, you need to end up having a phase value of the loop gain at omega equals to omega gx as minus 120 degree, resulting in a phase margin that is equal to 60 degree. Thank you.